Okay, looks like we are live. Thank you everybody for joining. I'm really looking forward to this session. I know this is something that our team has really been working on a lot. I'm really excited to bring this to you. So this session today, the title is Machine Learning Without Limits, Snowflake and Python Together in the Cloud. And we're really all talking about machine learning, scaling it up, making it run faster, learning, using larger data sets, specifically with Snowflake's cloud data platform, and then Python within Saturn Cloud's data science platform. So before we really jump in too much, we'll do some quick introductions. My name is Aaron Richter. I'm a senior data scientist at Saturn Cloud. And my work is really all about how enabling data scientists to do their work faster, better with the tools that they already know, and teaching them some new tools along the way. And my background is in data science, and I started in computer science, did a lot of kind of data warehousing, data pipelining work, dealing with large data sets, dealing with cluster computing, and then figuring out how to get that to work with data science and machine learning. So a lot of my work has really just been focused kind of in this space, and I'm really excited to be in Saturn Cloud and kind of promoting this tool that really helps make it easy for data science teams to do their work in the best way possible. And so I'm joined here also by Mike Harding, who is a senior sales engineer at Snowflake. And Mike, I'll let you introduce yourself.
Right. So I've been with Snowflake a little over 2 years now, and my area of focus is data science. And I've been in the big data, data warehousing, business intelligence space for over 20 years now, helping our customers be successful with either their migrations to the cloud or implementing data science projects. So I'm happy to be here today, Aaron, and looking forward to today's event.
Awesome, as am I. So the agenda that we're going through here, so if you haven't heard of Snowflake or Saturn Cloud, we'll make sure to give a good introduction to both of our companies and the solutions that we offer. So we'll start off with Snowflake and Snowflake's cloud data platform. Then we'll go into a little bit of really just Python data science in general, scaling that with tools, open source tools like Dasc and Rapids, and then how data scientists can do that within Saturn Cloud. And then what we're all here for is the Snowflake and Saturn Cloud integration. I'll show some slides and some code about how to do that. And then we'll also do a live demo of kind of a machine learning training exercise. So the first part, I'm going to hand it off to Mike for most of this, to talk about Snowflake's cloud data platform.
All right, thanks, Aaron. So the Snowflake cloud data platform powers 6 key workloads that drive business benefit through ease of use and its innovative architecture, and we'll get into that. Today, what you'll see is how our joint customers can leverage Snowflake to simplify and accelerate data science workloads, from integrating external data from the Snowflake Data Marketplace to performing feature engineering using simple SQL or external functions. Snowflake's unique platform helps reduce time to value for data science related projects. Next slide, please. All right. Snowflake runs as a service in the 3 main public clouds and delivers amazing capabilities by way of an innovative architecture. So Snowflake separates the storage layer from the compute layer to deliver a shared data multi-cluster architecture. So let me go into these 3 layers in a bit more detail. So first, that outermost layer called Cloud Services is managed by Snowflake, and it provides key services like metadata management, security and governance, and it manages the compute layer among other services that are depicted here. Now, the middle layer is the compute layer, which doesn't host persisted data like traditional MPP does. So compute clusters can be spun up and down and scaled up and down on the fly and used to isolate workloads that all operate on the same data depicted here in the innermost layer. So a data science workload can be isolated on a dedicated compute cluster to avoid slowing down other workloads like data ingestion or business intelligence. But every cluster reads and writes to the same data objects. So today you'll see some of Snowflake's capabilities made possible by this architecture, but there's so much more. So I encourage you to further investigate how Snowflake can help modernize your data infrastructure. And next slide, please. All right, so there's a bit of a build on this slide. So Aaron, I'll hand it over to you to cover the next concepts, and I'll be there to assist you if there's any areas that you want me to comment on.
Absolutely. Yeah, and so the great part here about Snowflake's data platform and kind of what they've built there and that kind of rapid scaling up of compute is that for in this particular scenario of feature engineering we're talking about, but just in general, when you're thinking about data science workloads, a lot of the work happens in Snowflake. And this is just like a really kind of toy example, but you'll kind of see where that value comes in a bit more. So the idea here is that your data is kind of managed in Snowflake. All the compute is there. You're working in SQL, right? And so you write a SQL query that can pull some data from a particular table. You might, in this case, is showing an example of feature engineering, is you might do things on a column like compute the average. But you might also do some more heavier things like doing a group by or an aggregation. And so the reason why it's really helpful to do this inside of Snowflake is that Snowflake SQL, first of all, is super fast. So it's going to execute this a lot really, really fast. And you don't necessarily have to pull all of your data out of the data warehouse into Python or kind of wherever you're doing your machine learning. So in this scenario, and we'll show you later in the demo, is where we're doing all of the feature engineering and kind of the data processing before the machine learning happens within Snowflake. And then we're only pulling through the data over the wire that we need to within Python to do the machine learning. And there's a great talk at Snowflake's Data Cloud Summit that they did just a couple months ago, talking all about how Snowflake fits into kind of this data science workload and streamlining data science. So I would definitely encourage you to check it out. You can watch it for free at this link down below. And we'll be sharing all of the slides that we're doing in this presentation as well. If you don't have a chance to kind of grab this link, we'll share the slides link towards the end of the presentation so that way you can grab all the resources that we're talking about here. Okay, and so now we'll talk about Saturn Cloud, but then specifically more about like the data science in Python and how we can accelerate and scale that stuff with open source tools. So I kind of always like to start this off with just like the kind of the traditional playing field of data science with Python. And Python is really a go-to language and really ecosystem for doing data science because it has all these great packages that data scientists trust, have used for years, and work really well for all of the things that we need to do. So those are tools like pandas, scikit-learn, numpy, and kind of doing your work with inside of a Jupyter Lab or Jupyter Notebook. There are some challenges, though, with these tools in that they were originally built for kind of single core, in-memory, like single machine paradigm. So there are challenges when your data set is larger than what can fit into memory, or when you have a lot of computations and custom code that you might need to execute that just takes a long time to run. And that's really where this conversation about accelerating comes in, is how can we kind of use these tools or APIs like these tools, and how can we kind of make our stuff faster or work with larger data sets? And there's really two options here. So the first option is, okay, if my machine isn't enough, maybe I'll get more of the same machine. I'll get 10 machines. And then now you're kind of thinking, RAM, so I'll upgrade to something with more RAM. Or I can try to get a faster processor. Or I can even try going to a GPU because those are a lot faster at processing. So those are kind of like the two things that you can do if you wanted to actually accelerate your data science work. And there are two great open source Python packages for doing this. And we'll go more into details if you're not familiar with these two packages about kind of what they are. But Dask is a parallel computing framework, which is kind of built in Python. And that enables you to do the first scenario, which is getting more machines. You can now kind of write code on one machine, but then it executes on a cluster of a bunch of different machines. And you don't really have to think too much about the cluster part. Rapids is a GPU data science library, which enables you to do all of the kind of traditional stuff like data frames, arrays, machine learning that you would do with like scikit-learn and pandas, but it's actually executing on your GPU instead of your CPU. So there's that concept of a better machine. You're still working with one machine, but now you have a piece of hardware that's a lot faster. And you can actually put these two together, Dask handling the parallel computing, Rapids handling the GPU computing to execute either if you have kind of multiple GPU cards on your single machine, or if you have a cluster of machines that each have GPUs, you can use Dask and Rapids together, and we'll show an example of that. But just a bit more into Dask and what it is. The concept of Dask is it being a distributed or parallel computing platform. It's built completely 100% in Python with the Python API. So you can kind of, if you're used to Python, you can go in, you can check out what it's doing. The key part and like kind of the framework of, or the kind of like base level of Dask is this lower level task library, which enables you to kind of parallelize any sort of arbitrary code and string together different pipelines, and then Dask will handle kind of distributing that to a cluster. And because of that, it actually has a large ecosystem of tools that are built on top of Dask or work with Dask. And that's what really makes it powerful. And if you go to dask.org, the website here, you can scroll down and see what's powered by Dask. There's a whole bunch of different Python projects that are using Dask, and you might not even know that it's using Dask under the hood. And then on the other side, there are higher level libraries built into the main Dask package for things like data frames, arrays, and machine learning, a lot of the common data science use cases, and it fits, again, within those tools and packages that I already mentioned that people are already using. It'll scale to your laptop to use all your cores on there, but it'll also scale up to clusters of machines. And so here's the concept of those higher level libraries that I talked about. So a Dask array is an object that essentially is a logical collection of NumPy arrays. And so those NumPy arrays, maybe the entire thing wouldn't fit into memory, but each of those little chunks will, and each chunk of this Dask array is actually just a NumPy array. So those are scattered across different nodes in your cluster. Computation will happen across the cluster, and then Dask will kind of figure out how to schedule and orchestrate that. Whereas you, the user, is just working with an array the same way that you would work with a NumPy array. Same concept works for data frames. A Dask data frame is a collection of pandas data frames. So you can peek under the hood, but also key thing is that the APIs are very similar. So if you're used to using pandas, you can use a Dask data frame. If you're used to using an NumPy array, you can use a Dask array. And then this part is just a really, really simple example of the kind of lower level task interface that enables you to kind of create large graphs of tasks that'll execute, and Dask will kind of figure out how to schedule and execute things in parallel. And we're actually going to use a little bit of this. It's called Dask Delayed API later on, so I'll kind of explain how that works. But this GIF here is actually a cool example of something that Dask has orchestrated. It's actually a hyperparameter grid search. And so you can see all the pieces where maybe the data was being split up, but then you can see all the models being trained in parallel, and then you can see results being collected, and then finally the kind of final metric being collected at the end. So when we talk about kind of parallel or cluster computing, inevitably Spark kind of comes up in the conversation. So Spark, if you're not familiar with it, is a kind of cluster computing tool that came out of the kind of Hadoop world and was built a lot in kind of this data engineering paradigm. It has a Python API, but it's built in Scala. It runs in the Java virtual machine. And the first challenge with that and the way that it was written is that if you're kind of a Python data science user and you're used to packages like pandas, scikit-learn, the first thing that you would have to do is rewrite all of your code into Spark, even if you just wanted to kind of parallelize like one portion of it. So that's a challenge, and that's why we favor Dask, because Dask is kind of Python native, was built out of the Python ecosystem, whereas Spark was built in a slightly different world for a slightly different set of users, and it has this Python API where it's kind of trying to bridge over. Another key challenge with Spark is that its programming model isn't really suited for the types of operations that would happen in data science. Specifically, multidimensional arrays are really something that's just kind of not really possible with Spark's programming model. Again, it inherited a lot of it from Hadoop and that MapReduce paradigm. And then certain things like machine learning kind of leave some things to be lacking. Debugging, monitoring it can also be challenging, again, because you're kind of having to jump through different layers into Scala or into the kind of like Java execution. And so that's kind of why we favor Dask. And so if you're interested in really learning about Dask, but also learning about Dask like with machine learning in mind, we did a workshop just a couple weeks ago where we went through and started off with like a single node scikit-learn workflow, showed how that started to fail with larger data sizes or more computations, and then showing how you can kind of get going on Dask, some of the main concepts of Dask, but then also getting to actually doing your machine learning pre-processing and model training within Dask. Okay, on to Rapids. Oh, and I failed to mention at the beginning, if anybody has any questions, feel free to put them into the event or the stage chat here on Hopin. We'll get to all the questions in the end, and I'm sure I'm sure we have some colleagues on there kind of answering your questions as you might need it too. Okay, next tool. So next tool is Rapids, and this is a really exciting tool. It's one of my favorite packages in the Python world because it's GPU accelerated data science. And it's a Python API. It's built, integrates with the Python ecosystem again, but it has native packages for data frames, arrays, machine learning, any types of other stuff that you might need to do in data science. And the key is that it's not executing on the CPU like most other things on your computer or libraries that you would be using. It actually executes on a GPU. And it's just way faster just because GPUs are faster at this kind of number crunching stuff than CPUs. And that's really been shown the last few years through deep learning, right? Tools like PyTorch, TensorFlow that are actually taking advantage of utilizing GPUs. And we wouldn't be where we are with deep learning if it wasn't for the acceleration that we got from GPUs. And I really think that the GPU data science, which is bridging, more than just deep learning into data frames and all the other stuff that you would do, is representing a similar paradigm shift as far as like the performance of what our data science code can do. And like I said, it actually can scale to clusters with its native Dask integration. So this is the first thing that convinced me that this GPU Rapids thing was something to watch and was a really interesting package that's going to really change the way we do stuff. So the second cell here that I'm showing you is just a typical pandas read CSV, right? This CSV file itself is like 600 megabytes, I think. And so that's like a standard thing that you would do. It takes a few seconds because you got to parse the CSV, parse through the lines, load it into memory, on all that stuff. The top cell here is with cuDF, which is the Rapids data frame library, which has API parity with pandas. So it looks and feels just like pandas. The read CSV command is the same. But you can see here, reading the same exact CSV file is 20 times faster. And I mean, that's just loading a CSV. That's just parsing, doing I/O, loading into GPU memory. That's not even doing anything yet, like a group by or a join or anything. And so you can imagine kind of all the other operations that you might do just happen a lot faster on a GPU. And so we at Saturn did a case study with this, looking at like a distributed random forest with a large data set across the cluster. So we were using 300 million rows. And we used a Spark cluster with CPUs for the execution. And then we did a Dasc and Rapids cluster using GPUs for the execution. And if you look at the bottom right graph here, that's the number there is in seconds. But to train just a single random forest model, I think it was like 100 trees, that took over 30 minutes on the Spark cluster. Whereas on the Rapid cluster, it only took 1 second. So the bar doesn't even register on the graph here. And so that's like a really big paradigm shift. Imagine having to wait 30 minutes for each model training, or just having it in a second, the same way that you would be used to with smaller data sets within scikit-learn, kind of just in your regular mode. And you can check out this blog post and check out the code there. I'll have a link to it again at the end of the deck. But I'm hoping this is kind of just like blowing your mind a little bit about how fast GPUs are, and the fact that you can actually use them for your machine learning, right? And so if you're interested in a little bit more, we did a webinar again a couple of weeks ago with Mike McCarty from Capital One. It was focused a lot on XGBoost, but we show an example of doing like a distributed kind of XGBoost training on GPUs and showing how much faster that is. So you can go ahead and check that out too. Okay, so this was just a brief intro to Dask and Rapids. There's a lot more resources if you want to learn about those specific tools. But the great thing about this is these are completely open source packages. You can go grab the code, get it yourself. You can contribute to it and get going for, again, Dask for parallel computing, Rapids for GPU computing. The challenge, though, is that the software here is free and open source, but hardware isn't free and open source, unfortunately, right? So the challenge is, okay, how do I actually get a cluster? I want to use Dask. How do I get a cluster? I want to use Rapids. How do I get a GPU? How do I get multiple GPUs? And how do I set those up? How do I provision things and install all of my packages? And so even if you're on the cloud like AWS, you kind of still have to think about spinning up your machines, security, I/O, all that stuff between them. And data scientists are not really meant to do that, right? Data scientists are meant to look at the data, analyze it, and train models, not to kind of set up machines and handle infrastructure. So that's where Saturn Cloud comes in. We manage all the infrastructure that you would need for running Dask or Rapids, and you can kind of just get up and running. You can spin up a machine, with 500 gigs of RAM. You can spin up a 20 node cluster, and you can spin up, a machine with 8 GPUs, and then you're just paying by the minute, right? And we kind of have two different kind of deployment options, as we'll talk about. But this is kind of the general infrastructure. We're pretty storage agnostic, so you kind of pull in wherever your data happens to live. And then we have a Jupyter Lab workspace for you to kind of use, again, the tools that you're familiar with using as a data scientist. But then you can hook in a cluster, or you can launch this workspace on a machine with a GPU, do all of your work there, get all of your accelerated model training. And then when it comes to actually deploying, you can deploy a REST API with a model, or you can deploy some sort of dashboard, or even like a scheduled data pipeline that needs to run on a recurring manner. But that kind of all happens within this platform. And this is a screenshot. I'm going to show you a demo of the platform, so you don't have to focus on this too much. But the idea here is that we center things around a project. You can launch up a Jupyter server for you to do your work, and then you can attach a cluster if you need to scale out. And then the deployments are made really easy for you to kind of keep going. Okay, so now to what we're all here for. We talked about Snowflake, what Snowflake does, how awesome they are. We talked about Saturn. We talked about Dasc and Rapids, data science in Python, how awesome all of that is, right? And now the real awesomeness comes from putting both of them together. And that's what I'm really excited to share here. And so if you want to read more, there's a blog post that Snowflake put out just a few days ago, kind of talking about this partnership that we have. Our goal is really to bring faster data science to the masses. And I think Snowflake and Saturn Cloud together make that really, really easy. And it is really a great architecture for doing that. So definitely check that out. Some of the code that I'm going to go through here is kind of illustrated in that blog post. But thinking about kind of like a high-level architecture of how this works with Snowflake and Saturn Cloud together, this is kind of what we put here. So you have Snowflake's cloud data platform, like all of the stuff that Mike mentioned. The data management is all kind of unified. You don't have to kind of like worry about coupled compute and storage. The data marketplace is a really easy way to get and share data. You can do all of your analytics, all of your queries that you probably already have a team kind of using Snowflake every single day for all of this stuff, right? And then on the other side is Saturn Cloud's data science platform, which I kind of just introduced that section. And so that's where you're kind of jumping into Python. You're running pandas, NumPy, Dasc, Rapids, right, to do all of your work. And then bridging them together is through the Snowflake Python connector, because Saturn Cloud is fully Python, any Python stuff, it'll work in Saturn, right? And so where this interfacing happens, and what's really compelling for the machine learning part, is when you have data in Snowflake, you need to do some transformations, right? And then pull it into somewhere to do the machine learning. If the data is kind of too big to fit on a single machine, you kind of need to scale up, right? And so with Saturn, you can now pull your data onto a Dask cluster to kind of do parallel computing, or you can do the kind of GPU acceleration. And through the Python connector, you can do that, feature engineering in Snowflake SQL. The data comes over the wire into Saturn Cloud. You're only transferring the data that you need to. And then, you're running experiments, you're training models, maybe you're doing some batch inference or something like that. You can then write kind of whatever you might need to back into Snowflake. So this is a really nice pattern to where all of your stuff that you need to do in your data science kind of workload happens between these two tools. And then so really kind of the next few parts is showing you just kind of how this actually works. We'll show some code about just the kind of standard way of you might load into pandas, which if you're kind of done a data science and have pulled data out of Snowflake, you might have already done in the past. But then we'll show how to actually do it into Dask and Rapids with Dask 2 within Saturn Cloud. Okay, so here's the pandas part. So this is going to be for you maybe smaller data sets. And you can totally do that within Saturn Cloud. You can kind of just launch up the Jupyter server, and then this will be on your single machine. So this is how the Snowflake Python connector works, right? Within this connector.connect function, you're going to have to pass in some arguments like your account name, username, password, that kind of standard stuff. And then you would execute some sort of query here. This is just a toy query that's not actually real that I'm showing. But then you can basically grab a data frame from that query. And this fetch pandas all method is really important, because under the hood, this actually utilizes Arrow for the data exchange. So it's really fast. having to worry about a lot of kind of serialization overhead. Arrow will kind of handle all that stuff. So that's going from Snowflake through Arrow into Pandas, and in this case, executing inside of Saturn Cloud. So, okay, that's good, pretty straightforward. The next part now is, okay, let's say your data doesn't fit into a Pandas data frame. That was the whole kind of challenges that I was talking about earlier, is that you would have large, giant tables stored in Snowflake, but if it can't fit into Pandas, you're going to have to sample or aggregate, and that's not really the best scenario, right? So we want to be able to actually utilize the same richness and the same size and volumes of data that you have in your Snowflake databases, but then also do machine learning model training within Dask. And so there's a few more lines here, but I'm going to break this down and kind of show you how this works. If you want to step through it a bit more, there's a link to a blog post here. Again, we'll provide all of the resources later on where you can kind of look through that. So you see we're still importing the Snowflake connector, the same Python connector that we were using for Pandas. And this kind of illustrates the fact that, again, Dask is built around and works with Python packages like Pandas. And so the first thing I'm going to show here is that we tweaked our query a little bit. So instead of in the Pandas one, we said only grab the first 10,000 rows because that's all that's going to fit into memory of the Pandas data frame, right? So now we're setting up a query, and this is using a binding from Snowflake. And so what this is saying is that we're setting up a query, basically a template, where we're going to pass in different values for this between clause. So that basically what we're doing is we're setting up the query to be able to load chunks of the data that I want. So I'll say 0 to 10,000, 10,000 to 2,000, 2,000 or 20,000 to 30,000, that kind of thing. And this would depend kind of on the nature of your data. You might use a timestamp column. You might use some other column, but the ID column is the easiest way to kind of think about this. So, and you would probably get your chunks some other way. Again, you know the nature of your data, so you might group it by month or by day or something like that. The blog post here actually has an example of like an automated function that you could run that will automatically grab the chunks that you would need. But you can kind of look at the blog for that. So then the key here is using this Dask delayed function. And I think I introduced that really briefly in a slide earlier. But what this is doing, and this looks a lot like the Pandas code that I showed you a couple slides ago. It's using the Snowflake connector, right, with this connection. It's executing a query, except this time now we're passing through two values for the binding, so the start and the end of our query. And then we're using that same fetch pandas all function. But we put this Dask delayed decorator on this function, and what that's telling Dask is saying, when I call this function, don't actually execute it right away, but actually build up a graph of tasks and then execute all of those things in parallel when I ask for them. And so that's what's happening here. So we see a list comprehension basically calling this load function for every single chunk that I have. So it's going to say load chunk 0 to 10,000, load chunk 10,000 to 20,000, load chunk 20,000 to 30,000, all of those things. So this is building up a list of what's called delayed objects. So Dask is basically figuring out the tasks that you want to do, but it's not quite actually executing it yet. And then this from delayed function is a helper function within the Dask data frame interface that is saying, I'm expecting a list of objects that resolve into a pandas data frame. Because remember, the pandas data frame is the building block for a Dask data frame. Each little chunk or partition is basically just a pandas data frame. So this from delayed function will understand that these pandas data frames need to be logically organized into a large Dask data frame. And then now you get this, you can't see that word, but that's DDF object, which is a data frame. It's a Dask one, so it's actually executing across the cluster, but it has all the same operations that you might want to do with a pandas data frame, except now it's with your large amounts of data. So this is the key critical part of where now you can actually use the data that wouldn't fit into pandas, but you can still kind of use Snowflake for all of the query stuff. So you wouldn't normally do a select star. You would do like select a column and do some transformations and maybe a group by, or, again, depends on the nature of your data. Okay, so bear with me, we got one more. This is now using Dasc and Rapids for the GPU acceleration. So Dask by itself is going to be executed across the cluster. It's going to execute on the CPUs, kind of just that normal way of executing. But like I mentioned, Dask and Rapids are integrated together where you can actually do this with GPUs. And it's not that much different. So a couple key differences you're going to notice here is I'm importing a couple different libraries, but again, they follow the same APIs as pandas and Dask data frames. So they're you can kind of just swap them in and out. And then the only change in my code here is once I have my kind of regular pandas data frame that's in kind of this CPU land, you can use the Rapids QDF from pandas function to take that CPU pandas data frame, convert it into a GPU QDF data frame. So now when I return that, it's going to return a whole bunch of GPU data frames. And then now this final data frame after I call the load function and the from delayed is actually going to give me now a collection of GPU data frames all stored on the GPU. So of course, another key difference in this scenario is that you're going to have a cluster of GPU machines, which Saturn Cloud comes in, makes that really easy. So like I mentioned, if you want to check out more about these details, I know I kind of breezed through that, and there's a lot of kind of details there and things to think through. Definitely check out this blog post, and we have a documentation page specifically about this Snowflake integration and how you can do all of these things. So you read through that, grab the code and look at the examples, and I think it'll really make sense for you. But with that, I think we're going to jump into the demo. Mike, was there anything else that you wanted to add before I go into the demo?
No, so far so good.
Okay, awesome. So now it's code time. So I'll show you a bit of what our data looks like in Snowflake, and then I'll give you a quick tour of the Saturn Cloud interface, and then I'll show you kind of the code and the example of the machine learning model training that we're doing here. Okay, so here is Snowflake, and I think everybody can see that okay. If anybody can't read that, let me know. I can zoom in one more. Okay, so here we go. I have this New York City taxi database where I've loaded in some New York City taxi data. So if you're not familiar with that specific data set, what it is each record is a taxi ride that took place in New York City. And so they have this data from like the last 10 years. And I've gone ahead and loaded that into Snowflake. We have some code for actually loading the data. The original raw files live on S3, but then there's some Snowflake SQL code that'll actually load this straight into Snowflake. But for now, we can see and preview. I'm just going to be using this taxi yellow table, which just, again, it's one row is an individual taxi ride. So we can see things like the trip distance. We can see the pickup zone and drop-off zones, and those are going to be some key features. And then we can see like how much money the taxi ride cost, and we can see like the tip amount. So what we're going to be doing in this particular machine learning exercise is we're going to predict whether the tip is a high tip. So like if the rider happened to tip more than 20%, or really we're predicting, is the rider going to give a high tip ride based on maybe the pickup location or some attributes about the pickup time. And so the first thing that I would want to do here is I've already set up a separate warehouse for my demo work. So within your kind of Snowflake and the way that your organization works, you might have different warehouses for different groups of users. Maybe your data science team has a specific warehouse. So it's been suspended, but I'm gonna go ahead and resume it. If you would run a query, it would kind of resume it and spin up automatically anyway. And then also one extra kind of safety measure that I'm going to do here and is really kind of useful for when you're doing these exercises is I'm going to create a clone of this New York City taxi database. So I'm not actually writing any data right now, but in your workload, you may end up eventually want to write some data. So in this case, I can create a clone of the database to give me an isolated kind of workspace. And what's great about this clone command is that it's a zero data copy clone. So we're not having to like copy over data and kind of mess with all that storage stuff. So in this case, I'm just going to go ahead and run this command to create my clone database, and that should run fairly quickly. And then now I'm going to use this New York City taxi_demo database to do all of my work. So in this case, I'm just going to see how many rows we have on the table, and we've got 300 million rows. So pretty good large data set to work with. Okay, so we'll come back and bounce back to Snowflake here to show some queries that are running. But first, I want to give you a quick tour of Saturn Cloud. So this is the Saturn Cloud interface, and here I'm showing you one particular project within Saturn Cloud. So When you sign up for Saturn, you'll actually get a couple different example projects kind of pre-packaged for you. And this is just so that way we can show you kind of how Saturn works, how you're able to kind of accelerate your workloads. But if you haven't even started in Saturn, the easiest way to do that is just go to saturncloud.io. And if you click Start for Free right here, we have a hosted platform. Our product is called Hosted, which means that you can just kind of put in your email username, and then you'll get a free trial. And once you exhaust all of the credits in your free trial, you can hook up a credit card and then kind of keep running and keep going. And then if you have a team that kind of needs a more enterprise, like secure, dedicated installation, we also have an enterprise product for that, which you can get installed within your own AWS account. But this hosted product is the best way to get going quickly. You can just put an email, and then you can actually run the example that I'm showing you today. You can run the exact same example for free kind of yourself within your Saturn account. So when you get into the project pane, you'll see this kind of examples GPU project that I'm showing you here. And this one is really illustrating a lot of the kind of GPU accelerated stuff that you would get. So there are two main hardware or types of hardware resources that you're going to be working with within Saturn, and that's a Jupyter server and a Dask cluster. So the Jupyter server is the part where it's a kind of a single machine that's running your Jupyter lab. And so you can choose any type of machine that you would want here. In this case, I've chosen a machine that has 4 cores, 16 gigs of RAM, and a GPU. And so that's important for our GPU acceleration. But you can get machines with up to 500 gigs of RAM, 4 or 8 GPUs, and then you can kind of use that with just Jupyter Lab, and then you're off and running. And then you also can attach a Dask cluster to this particular project. And so this is where you get that scaling out factor. And again, the workers for your Dask cluster, which is all the different nodes in the cluster, you can choose any instances that you want. It can have 500 gigs of RAM each. It can have a GPU. It can have multiple GPUs on each of your nodes. In this case, I have 3 workers, each with a GPU. But then you can scale up to 20, scale up to however many machines that you would want. Again, just depends on your data size. In this case, I'm showing you kind of a smaller example. A key part of this also is that every project is backed by an image. And so we have pre-created images. They're Docker images under the hood, but you usually don't have to think about the fact that they're Docker. And these are your Python environments. So we have environments here that have pandas, Dasc, Rapids, TensorFlow, PyTorch, like all of those things kind of already baked into the image. You don't have to worry about installing the packages. But if you have your own kind of custom environment that you want to bring into Saturn Cloud, you can create an image, put all the packages that you would need right into there. And then I mentioned deployments. If you wanted, let's say you did a bunch of code, you trained some models, or you're building a dashboard or a pipeline, and you want something to run, either have it be always on or have it run on a schedule, you can click here and create a deployment, and it'll use the same image, hardware that you choose, the code that you are running within your project. But I'm not going to go through deployments too much today. So with that, I'm going to go ahead and jump into the Jupyter Lab. My server and my Dask cluster are already running, and you can kind of hop into Jupyter Lab here and get working. So this particular project is kind of our example GPU project. And you can kind of run through this README, and you can see all the different things that you can learn with this particular example. But for now, I'm going to really just focus on this New York City taxi data with Snowflake, and I'll pull up a couple notebooks. So first, I kind of want to run through like the kind of baseline scenario of if you were just running with scikit-learn on a single machine, pulling your data from Snowflake, this is kind of the performance that you would get, right? But then we're really here for the kind of large data accelerated computing, which we're going to get with Rapids and Dask. So I'll go ahead and open those both up first. We'll run through what we're doing in scikit-learn. This code is going to look like a lot like that first example that I showed you, pulling data into pandas, and then the rest of it is kind of general scikit-learn. So here, we'll start off by connecting to Snowflake, right? And so this is using that Snowflake connector, and you can see some of those arguments that that I skipped over in the slides. You're always going to need something like an account, a username, and a password. And these are kind of hidden away using the credential interface and the credentials feature in Saturn. So there's this credentials tab where you can add credentials for any sort of credential that you might need. In this case, I'm using Snowflake credentials. And then they get stored into any project that you create under your user. So now I don't have my username and password just in the notebook. It's hidden away, and I don't kind of set it once, don't have to think about it too much. And then in this case, I'm using that warehouse that I showed you and the specific database, this New York City taxi demo database, that clone one that I created earlier. And so here is now kind of a more fully built out query where you would do a lot of your feature engineering using the Snowflake query, executes in Snowflake, and then it's getting pulled over into Saturn Cloud using the connector. So here I'm pulling from that taxi yellow table. I'm loading it into pandas, so I want to keep the data size pretty small because I need it all to fit into memory. And then here's where I'm doing my feature engineering. So I'm picking a couple columns that I would need. I'm computing my class label right here, which is, like I talked about, the tip percentage. So if the tip percentage is greater than 20, I'm going to classify that as a high tip ride, and that's our class label that we're predicting. And then we can extract some features from the pickup date time. So it's mostly going to be where are they picked up, where are they going, and then stuff about the time of day or the year that it's being picked up. And then we'll see if we can predict high tippers from there. And so this is the same code I showed you before. We're calling fetch pandas all to use that arrow optimized routine. Now we get kind of a regular pandas data frame here. And then in this section, I'm just kind of selecting the column names of my features, grabbing my features and my Y column. And looking at a bit the nature of this data set, we see 7 million rows here. So that's a good amount, good number of instances for training. And then the size here is around 200 megabytes. So of course, you can kind of try to scale this up if you wanted to. And this is just some pandas, right? We're now looking at the data that we pulled through from our feature engineering. And this is what we got from Snowflake. Okay, and then we can kind of just come down here and then do our machine learning model training with scikit-learn. So I'm just using scikit-learn's random forest classifier, doing random forest with 100 trees and a max depth of 10. So even though I'm executing only on a single node, because this is with scikit-learn, scikit-learn actually allows you to parallelize to all of the processors or all the CPU cores on your machine. So you do get some level of parallelism, but you're still bound by the memory of this one single machine loading the data into pandas. And then now I just kind of train my data. And so on that 7,200,000 megabyte data set, this took about 4.5 minutes, right? And so now that's one single model. If I wanted to do some hyperparameter search or whatever, that's now 4 minutes times 10, 100, 1,000, right? If you want even more data, first of all, you have to make sure that it fits into pandas. That's going to be your first roadblock. And then the second roadblock, if you can load it, it's just going to take a long time waiting for this random forest model. And then if you want to jump into the examples, you can see more about saving models and checking the metrics and things like that. But right now, I'm just kind of focused on the model training portion. So that's kind of how, kind of like the traditional world, right? I showed you how you would connect with Snowflake. And so you got the Snowflake part to handle the big data there, but you're still limited when it comes to the model training with the big data. So that's where we're going to pull in Dask and Rapids to kind of do these things. And so I'm going to put these two notebooks side by side, actually, so you can see how much of the code is actually really similar using Dask and Rapids. So the first thing I need to do, this is one part that's new. You can read through these notebooks to kind of, that'll describe a lot more of the details about what's going on under the hood. I'm kind of just breezing through and showing you the highlights. So the first thing here is connecting to the Saturn cluster. So if I bump back over to the Saturn UI, I can see that I already have a cluster running. It's using this machine that has a GPU, and I have 3 workers. If it was off, I could click this play button and then start it up. But here, using this Dask Saturn package is the way that you connect your Jupyter notebook and kind of connect your kernel or your current session into the cluster that's already running. So I can run that, I get my cluster connected, and then I can see some kind of information about my cluster. I have 3 workers, and across the cluster, I have 46 gigs of RAM. Okay, so that's just kind of making sure that my session is connected up to my cluster. Now, when it goes to connecting to Snowflake, this part is going to look pretty similar to what I showed you on the other notebook. This is actually almost exactly the same, right? It's the same kind of connection with Snowflake. We're using the same code. I'm using the demo database here. Okay, so now when I go to load data, I'm just going to show you the SQL query again, which again is very similar. The difference here is, like I was talking about in the slides, is you kind of have to think about how you're going to chunk up your query, because I'm not going to be able to load, my full data set that I want with just one single call, because it's going to overload kind of the pandas data frame. So we have to tell Dask, hey, here's how you're going to load different chunks across different nodes on my machine. So what's different here is in my where clause. So instead of saying grab me one whole month, I'm going to say grab me one specific day. And then that's what we're going to be using for our chunking. In the example in the slides, I show you how to chunk by like an ID column, like an auto-incrementing ID column. In this case, our data set is using a timestamp that's like fairly evenly distributed. So like taxi rides are happening every day, right? Weekends might have a little bit less, but in the general scale, each day is going to have a similar number of rides. If your data set was more kind of not evenly distributed across days, you might not want to do this, because again, you want your data to be like evenly distributed across your collection. And I'm going to pull this over so we can see this a bit better. And then so here's my Dask delayed function, like I introduced before. So I'm calling my fetch pandas all by passing in the day that I want, and then I'm just calling my from pandas. And so this is where I get the data frame on the CPU, and this is where I get the GPU data frame, because it's converting from the CPU pandas one into the cuDF GPU data frame. And so if you were doing some kind of like benchmarking, Snowflake has this really great feature where it will cache any queries that you run. So like if I run a query once and then 10 minutes later I run the same query, it doesn't actually execute the query again. It actually keeps those cache results and just gives you back the cache results. So it makes queries a lot faster. But if you really wanted to do some like performance testing, you might want to turn off the cache just so you actually have it re-execute the query every time. In this case, I'm not actually doing that. But I think I forgot to run some cells. Okay, let me run this one, and then I'll run this. So now we haven't quite done anything yet. We're just setting up our function to do the loading. Whereas on the other side, this would have already triggered loading the data frame. Okay, and here is just a helper function that I wrote basically to grab like all the different dates. So I could have just taken a calendar and say, give me January 1st, 2nd, 3rd, whatever. But in the event that there was a day that was missing, I want to make sure that I'm only grabbing days that exist in the data set. Otherwise, I would have empty data frames. So all this gives me at the end is just a plain Python list with all of the dates that I'm looking for. Right. So in this case, we're still doing the single month of January. You could expand it to, and this one I commented out here, I'm showing you 3 months. You can expand it to a year. You can expand it to a lot more data. I'm just doing the same single month just to illustrate the kind of performance versus the single node version. So here now we have 31 days in January, right? And this is now my from delayed function. So I'm going to call load for each of these different days, right? So now this is calling this delayed function. So I'm going to actually show you an example of like just calling it once. So if I wanted to call this just for one specific day, I can do that. And you'll see the output of this. Oops. See, the output of this is not really what you expect. It's not a real data frame, but it's actually a delayed object. And again, this is Dask building up your graph of all of the tasks. So in this case, I'm going to be calling this 31 times, and then I'm calling this from delayed function for the kind of Dask cuDF package, which is Dask GPU data frame package, to pull that now into this taxi data frame. So I'm going to run this, and this is going to take just a couple seconds. So this is not actually executing quite yet all of my Snowflake queries. What this is doing is Dask is figuring out what the logical makeup of my data frame is. So if I go to preview this taxi object, I can actually see the structure. Dask is saying this is a data frame that has 31 partitions. I don't really know much about the data yet because I haven't loaded it. Dask doesn't actually load it or execute those things until you tell it to. But I can go over here into the Snowflake query history, and I can see kind of what's been happening. So in this case, so there were some queries so you can see here, this is the date query that I executed before. But then you'll see that actually one of my kind of feature engineering SQL queries was already executed. This is because Dask needs to understand what the data types are and what kind of the logical makeup and the columns are of your data frame. So it didn't execute all of my queries, because there would be 31 queries, but it just executed one random query here just to figure out what the structure of my data frame looks like. So that way now it knows that I have all of these columns with these specific types. Okay, and so I'm going to go further down, and this is the same code. This is actually exactly the same code as from the kind of single node pandas version. This is just me collecting the features that I need, filling in some missing values, and so forth. And then right here, using this persist command is what actually is triggering Dask to go ahead and execute all of those Snowflake queries, and then pull all of my results into memory across my cluster. This persist isn't necessary, but because of the way that Dask does kind of lazy evaluation, is if you wanted like results from this taxi train data frame, it would actually go back and re-execute those Snowflake queries over and over again, which might not be horrible depending on the query because of the cache, but that's not really ideal. You don't want to keep sending all this data back over the wire and over the network. So I'm calling this persist command, which is telling me whatever graph of tasks that Dask has now, execute all of those, and then boom, keep them in my data frame. So I'm going to run that, and that's going to take a few seconds to run. So what I can do now actually is jump over here to back into Saturn, and I can click on the link for my Dask dashboard, and I can actually see all these different tasks that are happening. So if you notice that, there's a bunch of different things here that we're running in parallel. And then it's kind of showing you how much data is stored here and there. And so if you had like a larger query, you would kind of watch and run and see this progressing. The other cool part is I can go back here now into my Snowflake history, and now I can see that there's a whole bunch of different queries that were happening in parallel. They're happening all at the same time. So if you were to load those in pandas or use batches or something like that, they would all have to happen like sequentially, and you couldn't load it kind of all together. But now we can peek at this queries and see, okay, this one was grabbing January 10th. This one was grabbing January 9th, and so on. And then so again, if you had more data, you can scale up your warehouse into being a bigger size. You could also do like a multi-cluster type work. And Mike, could you actually talk a little bit more about how the multi-cluster part would work?
Sure. So Snowflake can essentially spin up an additional cluster to support what we refer to as a warehouse in Snowflake. So the warehouse is where the work is actually being done. And you can set a minimum and maximum number of clusters, or you can let Snowflake spin up an additional cluster in support of concurrency against a single warehouse. And what it does is it tries to eliminate queuing of queries based on how busy a cluster would be. So for example, if one cluster starts getting busy, Snowflakes will spin up another cluster and essentially reduce the queuing and perform more queries concurrently. So you can either let Snowflake manage that, or you can set the minimum number and the maximum number of clusters.
Great, yeah, and that's super helpful. Again, this one is just 30 queries, but you could have hundreds or thousands of different queries depending on the size of your data and the way that you wanted to load this through. So having those multiple warehouses kind of doing all things in parallel would be really useful and make this like really super performant. So you're not waiting, because you're not waiting for the entire 10, 20, 30 gigs to get transferred at once. You're doing all of that in parallel, and so the time ends up being really quick. Okay, so now let me see if that just took a few seconds, right, to execute all those in parallel, kind of save that in memory. And then here we can kind of run the same commands and see, this is 7 million rows again, 200 megabytes. And then this taxi train data frame works exactly the same way as a pandas data frame. So I can preview my data, I can look at the data types, and so on and so forth. Okay, now we want to really get to the model training, right? So we're going to do a random forest. I'm going to scroll the scikit-learn part all the way back down as well to show you, again, that the code is really similar. Sorry about that. But the QML, which is the Rapids machine learning library, has a Dask submodule, which will have these kind of multi-node, multi-GPU parallelized algorithms. So that's this random forest classifier. Same arguments here. I can say 100 trees, maximum depth of 10. And then I can kind of initialize that. And then I call fit the same exact way. And the difference here is that this fit is going to be a whole lot faster than the other one. So this is 4.5 minutes versus 3.5 seconds. And so that's what, like over 200 times faster if I do my math right, something like that. It's a lot faster. And this one on the right will scale up much better to larger data sets. And just from my own experience, this runtime doesn't get that much slower even when you're working with larger data sets, because you're going to then work with a bigger cluster. You can distribute out more of the work. And so this is that huge, big paradigm shift from being limited on a single node, being limited, waiting for stuff to run, now able to kind of run this across the cluster and pull it from Snowflake in a really efficient manner within the Saturn Cloud. And so that's the whole demo. That's really the key of it, is to show how your code is very, very similar. You don't have to really change a lot of your workflow, but it can be a whole lot faster. So I do want to have some time for Q&A, but we'll share the link to the slides in the chat if it hasn't already been shared. But here are a lot of the resources that we talked about. So I know I threw a whole lot at you, but the goal of this was to kind of like get an idea of what's going on, and then you can kind of read more on yourself and learn more of your things. So thank you all for joining. There's a whole lot of links here. You can join our Slack community. You can shoot us email, find us on Twitter. We have events happening all the time. Our next event is happening next week, which is going to be a workshop about PyTorch and Dask. But I just wanted to thank you also, Mike, for joining. I'm hoping all the attendees had a great time here. But thank you, everybody.
Thank you.
All right. Bye, y'all. Any questions? Before I say bye, actually, let's check. So we will have a recording later on. Okay.
There's a request for deeper dives. If you want to learn more about Snowflake, you can reach out to your local Snowflake account teams, or if you reach out to us, we can get you in touch with your local Snowflake contacts. So if you want to try Snowflake, definitely reach out to us. We'll be happy to connect you with the right people. There goes my Alexa. Alexa, stop.
We do have someone was talking about some benchmarks with Spark. We do have some. This case study here at the bottom was showing kind of the Dasc Rapids on a GPU versus Spark on a CPU there. I see that there was some chatter happening already in the chat, so that's good. Okay, well, I don't see any more questions, but if you do have more, feel free again to reach out to us. You can join the Slack community. Mike is also on there, and we can kind of talk and keep this conversation going. But again, thank you everybody for joining, and have a good afternoon.
Thank you.